So are all you folks at home watching the video note? Haha, no. Yeah, we should live stream it. That would be so cool. Could have interactive. We could. Hang on, someone has a question. Yep.
What's your favorite Radiohead album?
My favorite Radiohead album still got to be OK Computer. I mean, I do like the Kid A and After stuff, but it all blends into one big mishmash to me, and I enjoy listening to it. But as far as sort of creative variety and innovation, I think OK Computer really nailed it. So that's my answer to what my favorite Radiohead album is. Any other questions? Okay, so why are not that many people here? Is this a prelim week for some? What's that? Oh. Yeah, David.
This isn't a question, but I figured out why eggplants are called eggplants.
He figured out why eggplants are called eggplants.
Yeah. So if you remember last year I asked you that question, you could cover it. It turns out when they're like budding,
yes,
they look like little green eggs, and then they get long and purple.
Ah. Okay, so now our eggplants are like those sort of big bulbous purple things, you know, and the French call them aubergine, which is just their word for purple. Okay, but say Southeast Asian eggplants are these sort of longer, narrower things. Now, do they look like the same egg shape coming out of?
I want to say yes,
but you don't know.
I mean, I would assume so.
Okay. So much for that. All right. Yeah, Varun. That I don't know. Yeah. That I don't know because aubergine is not sort of like the typical monosyllabic French color word like rouge and noir and things like that, you know. So maybe they did name the color after the plant. Who knows? That's an interesting idea. Oh, Alex can look it up for us. Yeah. Okay. All right. We have to talk about stuff, real stuff. All right. Anyway, we were wrapping up the general discussion of continuous time signals and convolution. So we defined convolution, and for continuous time signals, and en route to doing that, we isolated this category of signals that we want to deal with, these decent signals that have certain properties, certain nice properties that we did on Tuesday. And then we had all these criteria for existence. And by the way, this is not an exhaustive list of criteria. It's not as necessary. None of these is necessary for the existence of the convolution of two signals. Two signals can be convolved even when they satisfy none of the criteria. And we had a little chat about that on Piazza last night. And these are a lot like discrete time. But we had this whole new idea of decent signals, so the decent assumption comes in all of them. That's the big difference. And at the very end of class, I said I'd like to do one example in class of computing a convolution, and there are several in the monograph, but I just want to go through it on the board and tell you how I think about these things, and you don't necessarily think about it the same way, but I think it's good to follow through one example. So here's an example. Say you've got x1 equal to the unit step, and x2 is the signal that has specification x2 of t is equal to, I think I use 7 e to the 7t when t is bigger than or equal to 0, and 0 when t is less than 0. And you can write that as e to the 7t u of t for all t. So we want to figure out the convolution of those two signals. first off, how do we know right off the bat, boom, that it exists, that there's nothing to worry about when we try to compute it? Aiden. They're both right-sided, exactly. If you have two right-sided signals, their convolution exists and is a right-sided signal. So that's a good kind of check thing for us. If we come up with an answer that's not right-sided, we know we messed up somewhere. But we won't. So anyway, x1 convolved with x2 exists by, I think I called it criterion 2. Both signals are right-sided. So anyway, let's compute it. x1 convolved with x2 of t. The basic definition, x1 of tau, x2 of t minus tau, d tau. And that's for all t. And now let's plug in what x1 and x2 are. x1 is a unit step, so it's u of tau. x2 is e to the 7. x2 of t minus tau is e to the 7 t minus tau. u of t minus tau d tau. Still for all t. That's what we have to figure out. All right, the first step is to invoke the unit step u of tau. And that serves to cut the integral off lower limit at tau equals 0. So this is the same as the integral from 0 to infinity of 1 times e to the 7 t minus tau u of t minus tau d tau for all t. And that's because u of tau is equal to 0 when tau is less than 0, and u of tau is equal to 1 when tau is bigger than 0. So that's the first step. The next step is to invoke the other unit step. And here's the hard part. This is where it breaks into cases. U of t minus tau is a backward-facing unit step that ends at time tau equals t, if you think of it as a function of tau. So this integral has got to end, upper limit, at most, at tau equals t, because u of t minus tau is going to be 0 for tau beyond t. On the other hand, sometimes, for example, if t is less than 0, u of t minus tau is never equal to 1 over this range of integration, 0 to infinity d tau. So the whole thing comes out to be 0. And that's why it breaks into two cases. The two cases are integral from 0 to t, e to the 7 t minus tau d tau. And that's when t is bigger than or equal to 0, and 0 when t is less than 0. And this is because u of t minus tau is equal to 0 when tau is bigger than t, and u of t minus tau is equal to 1 when tau is less than or equal to t. And when t is less than 0, tau is never less than or equal to t over the range of integration 0 to infinity. So you're always at 0. When t is bigger than 0, the u of t minus tau is 1 for a while, but not forever. OK? So that's the hard part. And now it's just a matter of plug and chug with the integral. And I'm just going to do it like over here. Integral from 0 to t, e to the 7 t minus tau d tau. I would factor an e to the 7t out of that. And what remains in the integrand is e to the minus 7 tau d tau. And that integrates to this. You can do that out. I won't go through it in class. And so this becomes 1/7 times e to the 7t minus 1. So the bottom line is, that's the expression for x1 convolved with x2 of t when t is bigger than or equal to 0. So x1 convolved with x2 of t is equal to that thing. And when t is bigger than or equal to 0, and it's 0 when t is less than 0. And one can compactly write that as 1/7 times e to the 7t minus 1 times the u of t for all t. Okay, so that's a paradigmatic convolution computation. It's the kind of thing you run into all the time. And you ought to know how to do that. And not the next homework, but the one after that, you'll have a chance to compute some of these. Any questions about this example? It's a lot like discrete time. Again, in some ways it's easier because to me, like computing integrals like that is easier than summing partial geometric series. I don't know about you guys. Yes, you agree? All right. Cool. All right. So let's move on to, and there are more examples in the monograph, discrete time or continuous time LTI systems. And here's where things really sort of start to split away from discrete time, where we run into difficulties. And today we're going to meet the delta function. Okay? So you applied physics people who've been dealing with that forever. Well, ECEs have too as well, but anyway. So continuous time LTI systems. Okay, so what is a continuous time LTI system? The definition is going to be almost exactly the same as discrete time, except you can probably guess there's one additional word that appears. What do you think that word is going to be? Decent, yes. Okay, so here we go. A continuous time LTI system over F, I'm going to write it just the way I did in discrete time, consists of the following two things. First off, a set of input functions. So a set of x, we're going to call capital F's contained in f to the r, instead of f to the z, of input functions. And this set has got to have some restrictions on it. X is a subspace. It's got to be closed under taking linear combinations. Otherwise, we won't have any way of defining what linearity means. X is closed under shifting. In other words, if I take a signal in X and I shift it by any t0, that signal will also be in X. And X contains at least, what do you think it's going to contain? We always want to make sure our input sets are rich enough to accommodate our needs and applications. So what do you think is a bare minimum of stuff that has to be an admissible input function space, signal space? Yeah.
Is it every decent signal?
Not necessarily every decent signal. Yeah.
No, finite duration signal?
Not all finite duration signals. Put these two together. Yes, at least all the finite duration decent signals. Okay, so that's, you both had part of the answer. So this is a lot like the discrete time X. The only new thing is decency. And a mapping S with domain X that goes into f to the r. And this is going to be the system map, the input-output mapping. So the idea, S of X is the output signal when X is the input. And it can't be just any old mapping. It's a noisy eraser. First off, it's got to be linear. What does that mean? That means that if I take S and I operate on a linear combo of inputs, which, by the way, is always going to be in capital X because X is a subspace, I get the same linear combo of the individual outputs. And that's true for all C1, C2 constants and X1, X2 in input signal space X. That's the L part of LTI, and the TI part, S is shift invariant. And that says that S of shift T0 of any X is the same as shift T0 of S of X. And we know because X, the input function space, is closed under shifting, shift T0 of X is OK to plug into capital S. So that makes sense. And this is true for all X in the input signal space and T0. Okay, so everything, the rhythm is all the same as in discrete time, except now we've got this assumption. The word decent comes in. X doesn't contain all the finite duration signals. It contains at least all the finite duration decent signals. All right, so let's look at some examples. And again, these examples are going to be continuous time versions of our prototype example systems that we saw in discrete time. And so I'm going to whip through them just like a highlight reel almost, because you can guess easily the form that each of them takes just based on the discrete time theory. So here's some examples. First off, what do you think our first two examples are going to be? You guys are so shy, I swear. Okay, Balazs? Signal? System, yeah. There's two S words in this class. Yeah. And what's the other one that falls under this category? The identity, yeah, cool. The zero and identity systems. The zero system, I'm going to take X to be all signals, decent or not, finite duration or not, and S of X is equal to the zero, and that's the zero signal for all X in cap X. And the identity system, again, X is all signals, and S of X equals X for all X. All right, and now that we're in continuous time, we can think about circuits embodying systems like this. So if I have, here's a system in a box, all right, and in there is going to be an electrical circuit. David?
Is it that X equals F to the R, or is X contained in F to the R?
X equals F to the R. We have to, when we define what a system is, we have to tell what the input function space is. So I'm defining these systems for you. I'm saying, here's the zero system. Its input function space is all signals.
Okay.
And its I/O mapping is take any signal 0. Got it? Yep. All right, so we can think about circuits that implement simple things like this. So suppose the input is going to be a voltage source going into this box. And the output is going to be a voltage, S of x. What do I put inside the box to get the zero system? What's that? Nothing? Yeah, a short circuit. Boom, like that. What do I put inside the box to get the identity system? What's that? Yeah, you could an open circuit, like so. Or, I could be really perverse and say, like op amp follower, I don't know, like inverter follower, but I won't. Right? You guys want to see real circuits, don't you? No? Okay. Who did you have circuits from, most of you? Afshari. He's awesome. Pollock? He's old school. He and I came about the same time, actually. I came before he did. By a semester, a year, actually. Yeah. All right, so anyway, what do you think the next system's going to be? Scroll back. Yes, a pure time shift. Thank you, Nathan. Pure T1 shift. And this is, as opposed to a pure K1 shift, now we're in continuous time. And again, x is going to be all signals. And S of x is equal to shift T1 of x for all x. And T1 is given. It's a parameter of the system. So that's a linear time invariant system. And you could actually implement that using ECE ideas by putting a super long transmission line between x and S of x. Like longer than T1 over the speed of light or something like, I don't know what it would be, but anyway. Okay. And what's the next one going to be? Okay, you've all had plenty of time. Okay, it's going to be an averager of some kind. So it's going to be a causal sliding window averager. And here's the first one where I'm going to make an additional assumption on capital X. I'm not going to allow all signals in f to the r to be inputs. I'm going to let x be all decent signals. And the reason is that the I/O mapping for the system S is going to be an integral, and we want to make sure it makes sense to integrate something. And indecent signals, as we know, sometimes fail that test. So what is S? S from x to the f to the r is defined as follows. When x is in x, so for x in capital X, S of x has specification S of x at any time little t is 1 over cap t, and here this capital T, like T1 for the shifter, is going to be a parameter of the system, equals the integral from 1 over t times the integral from little t minus cap t up to big T x of tau d tau for all t in the reals. And cap t bigger than 0 is given. Okay, so what this does is it takes an input signal And the value of the output at any given time is the average value of that input signal over the previous capital T length interval. So this is a perfectly obvious continuous time generalization of this causal sliding window m-fold averager in discrete time. And it has the same function. It smooths things out, essentially. Okay? Yep, Aiden?
Just based on what you mapped.
In other words, why are we not including indecent signals?
No, why are we mapping to all of that?
Well, I mean, I'm always allowing S to have, that as a target space. And if S of X happens to be decent, awesome. Okay? But that just relieves us from the necessity of worrying about, is S of X decent? So that's a good question, though. Jay?
How would you end up with like an indecent signal?
You wouldn't. You wouldn't.
Could you like restrict your map to that?
You could. So let me try to satisfy you guys. Turns out S of X is decent for all X in capital X. And in fact, it's decent on steroids. It's continuous, as it happens. When you take the integral of a decent signal and have the time argument as one of the limits of the integral, you always get a continuous signal. It may have little corners, like it may have coming in flat and then ramp up and then ramp over, but it will be continuous. Like think about integrating a unit step. It's 0 and then it becomes linear. So there's a corner, but it's continuous. That's the kind of signal you're going to get out of this. And finally, what do you think the last system is going to be? The integrator, right. And we don't even... Integrator, I'm not going to tell you what capital X is right off the bat. So S, I'm going to tell you what it is, and then I'm going to tell you what X is. So this is defined as follows. For X in capital X, whatever capital X is going to turn out to be, S of X as specification, S of X at time t is the integral from minus infinity up to time t of x of tau d tau. And what is capital X? Capital X is just going to be the set of decent signals for which that integral exists for all t. And if we wanted to be super honest, we would have to go through and make sure that capital X satisfies the requirements on an input function space, that it's a subspace, it's closed under shifting, and contains at least all the finite duration decent signal. But I would contend that those assertions are obvious. So let me just wrap that example up. And cap X equals the set of all decent signals for which that integral exists for all t. And in fact, you only really have to check that the integral exists for time t equals 0, because for above t, decency means that that's always not going to add on anything infinite. But I prefer to say it that way because that's the way we said in discrete time. David?
I'm just trying to wrap my head around system stuff again. So could you consider convolution for every instance of the second, like, what do you consider a system where the first
Yes, and that's exactly the next thing I'm going to talk about.
Oh, cool.
Yeah. His question, by the way, for those of you like the ones watching at home, the many students watching at home today, who couldn't hear it, is the following. What if I have some signal H, say, and I define a mapping that takes every, say, decent finite duration signal and convolves it with H? Does that give me a system, an LTI system? That's kind of what you asked me. And the answer is yes, and that's the next order of business. Okay? So, good lead in. I think it's the next order of business.
What defines the system? Is it just the operator, or is it the fact that you already put it in input signal?
The system is the following. It's an input function space and an operator. Okay? That's what it is. Okay. Anyway, here's a far more general example. Of a linear time invariant system. And when I say LTI system, I always mean, in the context of this part of the class, a continuous time LTI system. Sometimes I'll just say system. It means the same thing. All right. I'm going to let H in f to the r be any decent signal. Any decent signal. Let script d sub h be the set of all decent signals x for which H convolved with X exists. Now, does D sub H contain every finite duration decent signal? No matter what H is? Okay, you answered my rhetorical question correctly. Whoever answered. Now you have to tell me why. Why does it contain every finite duration decent signal no matter what H is?
Is it because of the finite duration part of it? So because it's finite duration, you can convolve it with H, which can be n to A.
Yes, you can convolve a finite duration decent signal with any decent signal. So, no matter how pathological the H that someone presents you on whole plaza is, you can convolve it with every decent finite duration signals. So note, by criterion 1, if you want to be precise about your chapter and verse attributions, D sub H contains all finite duration decent signals. And furthermore, it's easy to show that D sub H is a subspace of f to the r and that it's closed under shifting. So also, and this is easier to show, D sub H is a subspace of f to the r closed under shifting. So now that we know those 2 or 3 or whatever factoids about D sub H, we know that D sub H is suitable as the input signal space for an LTI system. So now define a system by setting capital X, its input function space, equals D sub H, and system mapping S of X equals h convolved with x for all x. That's, I think, what you were kind of asking about. If someone comes up to you on the street and gives you at least a decent signal h, you can define a system just by setting the input function space equal to d sub h and defining the system mapping as h convolved with x. All right. Now, I'm going to introduce some terminology here. This kind of a system, remember, let's pause and think back to discrete time. In discrete time, essentially every system was a system of this kind. It was convolutional in the sense that there was something that you could convolve with inputs to give you outputs, and that turned out to be the impulse response of the discrete time system. And in discrete time, the impulse is an actual signal, so it makes sense to talk about the impulse response as the response to a signal. Continuous time, that's going to turn out to be a little iffy. So I'm going to define every system, the set of all systems of this kind, define a system of this kind as what I call strictly convolutional. So here's a terminology we're going to use. A system is what we call strictly convolutional when it is of this kind. And when I say when it is of this kind, I mean this is the noisy eraser. So that is to say, when its input function space cap x is d sub h for some decent h, and its system mapping is S of x equals h convolved with x for all x's in that set, capital X. So that's what a strictly convolutional system is. Okay, now in discrete time, these systems were essentially universal. And in continuous time, they kind of almost are. And we're going to have to pull apart which ones are and which ones aren't and all that kind of thing. And to get a grip on this, I want to look at the example systems. And I'm going to take a little poll on each of these systems. Do you think the zero system is strictly convolutional? Yeah. What about the identity system? How many think yes? How many think no? Yes? No? Okay, how about the pure T1 shift? How many people think yes? How many people think no? Okay. What about the averager? How many people think yes? You're not going to lose anything. You know, like you're not going to be shot at dawn if you get this wrong. Dude, answer the question. Do you think the averager is strictly convolutional or not? Yes? No? Okay. How about the integrator? Yes? No? Okay, I'm interested in the way that the responses to the last two diverged. Because in a sense, the averager, the integrator is just like almost like an infinite T version of that. Well, anyway, it turns out that the averager and the integrator are, in fact, strictly convolutional systems. And the zero system are strictly convolutional. And I'm going to tell you what their H's are. But the pure T1 shift and the identity system, which is actually a special case of the pure T1 shift, are not. Okay, so for the averager system, let's look at that one. The averager system its input function space was the set of all decent signals, still up there, and its I/O mapping S was defined by that. It turns out that S of x equals H convol with x, where H equals this. H of t is equal to 1 over cap t when 0 is less than or equal to little t less than cap t, and 0 otherwise. And I want to emphasize, once again, it doesn't matter how we define H of t right at 0 and right at capital T, as long as it looks like that. And x equals d sub h, which in this case is the set of all decent signals Y is the set of all decent signals d sub h for this h. What does this h look like? Looks like this. It's 1 over t for a while, and it's 0 otherwise. So Y is every decent signal convolvable with that h. It has finite duration. This is, just drill that into your firmware or whatever you have in there. That every finite duration decent signal is convolvable with every other decent signal. So whenever you see finite duration and it's decent, it's like all bets are off in terms of things not converging, things going wrong, whatever. And that should be reassuring because everything in our actual lives has finite duration, right? Including our lives themselves. Okay? I know. It's a bummer, eh? Okay. How about the... anybody care to hazard... Now this H looks an awful lot like a continuous time version of the H we had for the sliding window n-fold averager discrete time. What do you think the H that goes with the integrator is going to be? So for the integrator, S of x turns out to be H convol with x, where H equals what? What do you think? You're looking back at discrete time, right? Okay. What about Juxiang? Are you looking back at discrete time? Not really, but kind of. Well, thinking is good. That's what this course is supposed to be good for your head. Over the long haul. And that is also called, yeah, very good. And d sub h, we already defined the input function space for the integrator to be the set of all x's for which that integral converges for all t, and that's the same thing as the set of all things convolvable with h. So those two systems, as a matter of fact, are strictly convolutional, and the zero system is if with h equals 0. But I told you the other ones aren't, and I'm not going to prove that in class, but there is a proof in the monograph, very carefully done. It doesn't involve any advanced techniques. So proof in the monograph that no decent signal h exists for which h convolved with x equals shift t1 of x for all decent x. And that's true for any t1 in the reals, including t1 equals 0, which is the identity system. Thus, the shift system is not, in our terminology, strictly convolutional. Okay? But the shift system is pretty innocent, right? It's not the kind of thing you're scared of if you run into it on the street. I mean, I would be more scared of an integrator if I ran into one of them than I would of a shift system. So there's got to be a way to get a grip on that using this kind of thinking. So let's take the 3-minute break, and then we'll try to do that. Hey. Did you send it twice?
Yes.
Yeah, I got it.
Okay.
Yeah.
Also, I was wondering, sometimes you can write K0 or sometimes K1, T0, T1. What's the difference?
Discrete versus continuous.
Oh, I mean with the 0 and 1.
None.
Sometimes there's shift K0 or
Yeah.
sometimes there's shift K1.
Well, when usually I use the K0 when I'm talking about a general shift mapping, you know, and usually I use the K1 when I'm talking about the pure K1 shift system. Okay, that's all, you know.
All right.
Okay.
I just didn't notice any pattern.
Yeah. Well, that's the pattern actually.
Okay.
H is equal to U.
You don't get why what?
H is equal to U for the integrator. I thought if you
No, shut.
Well, yeah, I guess so. It's convolvable with every DC signal, I guess. How do we know that?
Okay. Right? And now I'm going to let zeta equal t minus tau.
Okay.
Okay? So d zeta is minus d tau. And tau runs from 0 to infinity, means zeta runs from infinity to 0. So another minus sign comes in to cancel this one. So this equals integral from minus infinity to t of x of zeta d zeta.
That's a power move. Thank you.
Power move, yeah. the cross dribble, right? You know.
For the integrator,
Yep.
we have the impulse response is the unit step.
Mhm.
How do we know that is convolvable with all of the
Because we define the set capital X to be the set of all things convolvable with U. Or we actually, we defined for the integrator, we defined the input function space x to be up there on the far upper left, this set of all decent signals for which that exists, which is tautologically, yeah.
So the integrator, like this, it makes sense that the integrator would work for any input signal. Okay.
And that you're allowed to use. Okay, so let's see how we approach these non-strictly convolutional systems. First of all, for a strictly convolutional system, I'm going to introduce a piece of terminology. So here's some terminology. The decent signal H associated with a strictly convolutional system So in other words, it's what you convolve with inputs to give you outputs in a strictly convolutional system is called the system's guess what it's called? Impulse response. Okay. Now, the cool thing here, or not so cool, depending on how you look at it, is that we have defined for continuous time systems, at least of this subclass, strictly convolutional ones, we have defined impulse response without having defined impulse. Okay? Whereas in discrete time, the impulse was an actual signal. So the impulse response of a system was just the output you got when you put an impulse in. But in continuous time, okay, why do we call it that? Why that name? And this is sort of a, so why call it that? Okay, so what I want to do is I want to take the system, I take a strictly convolutional system. So take the system and use the following as the input signal. It's going to be 1 over A times what I called PA as the input signal. So let me remind you what the PA was. So PA was this, was a unit pulse. This is PA of t. It was a unit pulse of height 1. That's what unit means, I guess. Centered at t equals 0. So it goes out to plus and minus a over 2. So that means that 1 over a PA of t looks like this versus t. It's just a unit pulse of height 1 over a centered at 0 that goes out to plus and minus a over 2. Okay? So 1 over a PA of t equals 1 over a when, say, minus a over 2 is less than or equal to t less than a over 2. And again, it doesn't really matter what's happening right at the corners. And otherwise, it's equal to 0. Okay, so we're going to use this as the input signal. And we're actually going to vary a, as you might imagine. So anyway, let the output that arises from PA, we're going to call that HA. So let HA, for each A bigger than 0, let HA equal S of 1 over A PA. So that's the output that arises. From that input. Now remember, we're talking about a strictly convolutional system. So the output corresponding to any input is H convolved with that input. So now, S of x equals H convolved with x for any x. Because it's a strictly convolutional system. Oh, and there's a missing D up there. The decent signal H associate with. That sounds really bad. It looks even worse. So I'm going to put the D on there. You just know that someone's staring at that when they're watching this video. There. So anyway, what is H sub A? So thus, H sub A is equal to H convolved with the signal 1 over A PA. Let's compute what that is. So H sub A of t is going to be equal to integral from minus infinity to infinity, H of tau, 1 over A PA of t minus tau d tau for all t. And because P sub A takes such a simple form, we can simplify that. Let's graph what P sub A of t minus tau versus tau looks like. So this is, suppose t is here, and this is tau space. This is what 1 over A goes out to t plus A over 2, and out to t minus A over 2, height 1 over A. This is 1 over A PA of t minus tau. And if you want a math expression for it, it's equal to 1 over A when t minus A over 2 is less than or equal to tau less than t plus A over 2, and 0 otherwise. So what does that do? What does that mean for H sub A of t? H sub A of t is equal to that whole integral that gets chopped off except for that tiny little space around t. And I get this, 1 over A integral from t minus A over 2 to t plus A over 2, H of tau d tau. Now, from Calc 1, or even Calc 1/2 almost, like an AB level calc course, you learned what happens when you integrate something over an interval and then divide by the length of the interval. What do you get? Yeah, this is the average value of H of t. So average value of H of tau on the interval t minus A over 2 to t plus A over 2. And you could have it open, close, whatever. What happens when I let A go to 0? What does that converge to? Remember, h is a pretty well-behaved signal. It's a decent signal, right? If I take the average value over ever narrower intervals centered on t and let the width of those intervals go to 0, what is that going to converge to? H of t, yes, h at the center of the converging intervals. So since h is decent, and here's one of those situations where since h is decent, the limit as a goes to 0 of that thing, ha of t, is equal to h of t. At least when t is a continuity point of h. And when t is not a continuity point of h, when it's a jump time, we don't care really what the value of it is. Remember, because the value of any decent signal at its jumps, you can assign it anything you want, it's never going to matter. And it turns out that it converges to the average value across the jump when t is a jump point. But we don't care. So essentially, for all practical purposes, the limit as a goes to 0 of ha of t is h of t. But what is HA? HA is the response to 1 over APA. So this is what we've got now. If we take the limit as a goes to 0 of the system operating on 1 over APA, we get h. Because HA is just 1 over APA, response to that. Now, this whole exercise started with that question there. Why call it that? If you have this decent signal h associated with a strictly convolutional system, this h is what you convolve with inputs to give you outputs. We call it the impulse response. Why call it that? Well, if you take this expression here and you violate every rule of math that you can think of, and you interchange the limit with the s, what happens? So let's be daring, or foolhardy, or reckless. Interchange lim a goes to 0 with s. And what you get? You get h equals s of limit as a goes to 0, 1 over APA. Okay, well, what's that thing inside the parentheses? It's not really a signal if you think about it, because what is 1 over APA? It looks like that up there. So what happens when I shrink a? It narrows down, it goes up, right? Narrows down, goes up. Narrows down, goes up. So when a is 10 to the minus 59th, that thing is only 10 to the minus 59th wide and 10 to the 59th tall. And you can see what's happening as a goes to 0. So what is this? This is a big question mark. Because limit as a goes to 0, 1 over a, pa of t, is equal to infinity, when t equals 0, and 0 when t is not equal to 0. And this clearly is not a signal. Signals are things that take on numerical values, and infinity doesn't count as a numerical value. So it's not a signal. But we sort of pretend it is, and we play around with it a lot. And so we're going to give it a name. So we're going to give this thing inside the parentheses a name. So we're going to give this non-signal a name, and that's just going to be delta, the continuous time unit impulse. And I'm going to give you a rigorous meaning for any expression wherein delta occurs under an integral sign in just a moment, after telling you a silly story. Okay, as always, have to throw one of those in, like, and you don't have to turn the camera off. This is SFW. Okay. Anyway, no. Anyway, so it's also known. This is also known as the Dirac delta function, right? And the Dirac delta function is named after Dirac, obviously, and Dirac has a French-sounding name. Right? And I told you that in this class we'll have German things that are all rigid and easy, to understand, and we'll have French things that are all kind of hard to understand and fluffy. So another name for the discrete time unit impulse, does anyone know what that is? What, Fred? What? Kronecker. The Kronecker delta. So that's Teutonic. It's rigid. And this is the Dirac delta, Okay, now ironically, Dirac was not French. He was English. His name was Paul Adrien Maurice Dirac, and he was very tall. And he's one of those people who, there's so many great stories about him. And in fact, there was a book that somebody published a few years ago about him, a biography called The Strangest Man. That was the name of the book. Okay, now, he's one of those people who folks have diagnosed retroactively as somewhere out on the autism spectrum, like Asperger-y kind of stuff, right? Has marked diminished social skills and everything. There's stories about him like someone went to visit him when he was teaching at the University of Florida. They went out to lunch. They sat there in stony silence for a quarter of an hour. His friend says to Dirac, "So, have you seen any good movies lately?" And Dirac looks up and says, "Why would you want to know?" He's that kind of guy. Anyway, he was Mr. Theory, too. Like when he saw the Schrödinger equation, which is at the core of quantum mechanics, he allegedly said, "After this, it's just chemistry." And you know how that made all the chemists in his social sphere feel, Oh, just chemistry, huh? So anyway, he was not very diplomatic. But, and he also was famous for having said that if you have a beautiful theory and someone does experiments that contradict the beautiful theory, then they should do those experiments over again because they must have been wrong. He was that much of a theorist. So anyway, that is the man behind this monstrosity, this non-signal that we call it, the continuous time unit impulse. And we rarely see it. It's an abstraction that's useful. It's always good to remember it's not a signal. It's more like an operator on signals. And if you want to do a rigorous treatment of these, you really have to do a kind of a Lebesgue measure sort of treatment. It's a point measure in Lebesgue measure theory. Or you can do it in the style of Schwartz distributions, from the early 20th century. And that's kind of passé. But the main thing is that delta is less a signal. It's more like an operator on signals, okay, than a signal, but we play around with it as if it were a signal. We put it under integrals, we change variables in it, we do all that kind of stuff with it. So we manipulate it. like a signal. As if it were a signal. That reads as if we manipulate it like a signal would manipulate it, but that's not what I meant. Okay, so here's a rigorous meaning. For any expression of the form integral, and the integral can be over any interval, minus infinity to infinity, or a bounded interval, or whatever. If you see a delta of tau and anything else, d tau, the rigorous meaning for that expression is lim a goes to 0, 1 over a, integral over whatever interval it was, pa of tau times that anything, d tau. Okay, so that we can give a rigorous meaning to any expression that has delta under an integral sign. Okay? Let's apply that. Let's let x be any decent signal. So here's an application. Let x be any decent signal. And what I'm going to do is I'm going to write down an expression that looks like this. So integral from minus infinity to infinity, delta of tau, x of t minus tau, d tau. So in this case, the x of t minus tau plays the role of the anything over here. Now, what does that look like? It looks like a convolution of two signals, but the delta is not really a signal. So what happens when we plug in the rigorous definition? It's the lim, as a goes to 0, of the integral from minus infinity to infinity of 1 over a pa of tau x of t minus tau d tau. And that's the same as 1 over a integral from minus a over 2 to a over 2. I forgot the limit there. Of x of t minus tau d tau. Right? And if you do zeta equals t minus tau, right? And so d zeta is minus d tau and all that kind of thing, this turns out to be the same as limit as a goes to 0, 1 over a integral from t minus a over 2 to t plus a over 2, x of zeta d zeta. And by the way, I almost always use zeta for the new variable of integration when I change variables in integrals, because zetas are fun for me to write. I don't know about you guys. I think the least fun lowercase Greek letter for me to write is xi, okay, or xi. I don't know how you say it. It probably depends on whether you're in a fraternity that has a xi in it, you know. But what does that come out to be if x is a decent signal? What does that come out to be? This looks an awful lot like that thing up there, except you have an x in there instead of an h. This is the average value of x over an interval of width a centered at t, and I take the width of that interval to 0. What does it come out to be? X of t, right? So what does this say? This says, and bear with me, I know I'm going to go like 30 seconds over here. This says that delta convolve with x of t, which is that first integral I started with, delta of tau, x of t minus tau, d tau equals x of t for all t. I'll put all in quotes because that might not include the jump points. And a quick way of writing that is that delta convolve with x equals x when x is decent. So, what does this mean? This means essentially that delta is an identity element for convolution. It's not a signal, but it's, if we think of it as something that you can put under integral signs with impunity, you discover that when you put it under there and you do a normal convolution, regular old convolution with it in there, use the rigorous definition of what it is under the integral sign, you get that. So one problem this solves for us is it gives us something to convolve with inputs to give the output of the identity system. We didn't have a decent signal to do that, but now we have something else to do that with. And that's what I want to pick up next time. Okay, so hardest lecture of the semester over with.